What's going on, everybody? My name is Will. I'm a student at North Carolina State University studying electrical engineering, and I thought I would do a lecture series on the cheap and dirty tricks of electrical engineering to excuse me, to hopefully help those of you who are considering going into electrical engineering to make the jump, and also to make it easier for those who are going into electrical engineering to absorb the material that they're learning in their degree. Sometimes it can be very difficult to get a grip on the process when you're busy processing so much information. So going into college knowing how to do circuit analysis, or going into some of your more challenging classes, like when you get to transistors, knowing how to perform the analysis already might actually help you understand the material in context. So that's what this lecture series is aimed to do. Now, given that this is going on my fire alarm page, I figure that most of you watching this video have some ties to that, and I'll do my best to bring a little bit of that, a little bit of where this is relevant to those who are in the field of fire alarm when I can. But for the most part, this is going to be more of a lecture-based series oriented towards preparing you for circuit analysis in college. So without any further ado, I think we'll go ahead and get started. There's a couple things that I want to outline here before we get started, a couple of important keywords and concepts to understand here. Starting with charge. Charge is a property of an atom, and as I am not a chemistry expert, I'll explain this as simply as possible. Electrons and protons are two subparticles of an atom. Electrons are negatively charged, or hold a negative charge, and protons hold a positive charge. Now, when we talk about charge here, we are talking about the atom as a whole. So what's the overall charge of an atom? And in this case, if it has more electrons than protons, we say that atom has a negative charge, and we say it has a positive charge if the converse is true. So more protons than electrons. The units for charge are coulombs, and the symbol that we use for them whenever we work with them is Q. Now, in this lecture series, we will hardly, if ever, work with charge. We might see it a little bit when we get to inductors and capacitors, but we really won't work with it all that much. And the only reason I'm bringing it up now is so that we can understand the derivation for voltage and current, given that they are based on charges. Now, voltage, speaking of the devil, voltage is a commonly used term in our lecture series here, and voltage is represented by a capital V in our circuits, and the unit for voltage is volts, which is also represented by a capital V. Now, volts is a unit of energy per charge. Energy is expressed in joules, which is where that capital J comes from right next to it. So joules per coulomb is where we get the volt from. Now, also an aside about energy. This is a more physics-oriented topic, so we won't really be working with energy too much, but when we get to inductors and capacitors, it'll be important to note that they are energy storage devices, and we will talk about that more in detail later, but keep that concept of energy on the back of your mind. Do some digging around. Next up is current. Now, current is expressed in amperes, or as we call it, amps, and this is derived from charges per second, or coulombs per second, and the letter we use to denote that in a circuit diagram is I, capital I. And next up, resistance, expressed in ohms, and also denoted by a capital R on circuit diagrams. It's dual, the unit of conductance, or which is expressed in Siemens or mhos. Now, Siemens is that capital S, and mhos is that upside down omega. Funny story, actually. I'll use my pointer here. This guy is just an upside down omega, and the unit for resistance is ohms, and the unit for conductance is mhos, which is just ohms spelled backwards. So electrical engineering, whoever invented electrical engineering apparently had a sense of humor. We will hardly, if ever, work with conductance, but it's just important to know where it comes from, because it may be useful in some physics applications. But the capital letter G is what we use to denote that. And a side note over here is that Siemens is equal to 1 divided by ohms. Next up on our list is the capacitor, or capacitance, which is expressed in units of farads, and we use a capital C to denote that on circuit diagrams. Now, this is one of our energy storage devices, and its dual, the inductor, which produces inductance, has units of henries, and we use a capital L to denote that on a circuit diagram. Now, last up is power. Now, power is not related to any circuit element per se, but it is a property it's a property or a unit of, it's a means of expressing energy and work. And it has the units of watts, which comes from joules per second. Excuse me. Which comes from joules per second. And we use a capital P to denote power. Specifically real power. There are multiple types of power, but we will get into that as we get further into the lecture series. All right. So now that we've covered some basic terms, let's go over some circuit components that are related to these. We'll try and go through these pretty quickly so that we can start talking about some actual circuit concepts here. These guys right here, these circles that have two legs on them, these are two terminal devices, and they are called independent sources. Now, independent sources come in two forms, voltage or current sources. Current sources are very difficult to come up with, but voltage sources are pretty common, like batteries or power supplies, whatever the case may be. And we will be using these exclusively in our circuits to supply energy or supply electrical current or voltage to a given resistive load. Now you'll notice that those same polarity symbols and the arrow are in these diamonds down here. These are dependent sources. Write that out real quick. Now, dependent sources are like independent sources in some ways. However, they are dependent upon another circuit element in that same circuit. And we'll see examples of this when we start working with more complex circuits. Now, there are actually four types of these. There's voltage-controlled voltage sources, voltage-controlled current sources, current-controlled voltage sources, and current-controlled current sources. But for simplicity's sake, we are going to say that this is K times some circuit value, and we'll just, for the sake of this, let's say for the voltage source, it's K times some other V in the circuit, or for a current source, it's K times some other I in the circuit, whatever the case may be. And of course, this is where the whole voltage-controlled voltage source, current-controlled current source thing comes from. But anyway, we will be seeing quite a few of those, particularly when we get to transistors. Next up is the resistor. Little squiggly line. Now the resistor is pretty self-explanatory. It has some value of resistance that helps us determine the voltage and current across it. We can use these to perform a wide variety of functions, from voltage division to current division to Wheatstone bridges and all kinds of other interesting applications for resistors. But we will not be focusing so much on the applications for the time being, as we are just learning how to work with these circuit elements. We will get into their applications a little bit later. Next up is an interesting one, the diode. Now the diode is not it's not like a resistor in the sense that it simply creates a current draw. The diode limits the direction of current flow, and it does have some potential difference across it, but we'll get to that when we start talking about the constant voltage drop model in semiconductors. Diodes are quite useful in power applications, as we often like to use them to build rectifiers. So keep that in the back of your mind. Next up is the capacitor. And we will see these a lot. Capacitors are quite useful little energy storage devices. Now these are like resistors in some ways, and very different from them in others. Resistors are what we call a purely linear passive component, where its voltage is in a constant linear relationship with the current and the value of the resistance. In a capacitor and an inductor, that's not necessarily the case. It takes time for these units to charge up and discharge, and we'll see that when we start talking about DC switch circuits. Inductors are similar to capacitors, they're almost like the opposite of capacitors in some way. Again, we'll talk about that later. But these are just some symbols to get familiar with so that you understand what you're looking at when you're looking at it. Now let's get some basic formulas out of the way. Start with Ohm's Law. Ohm's Law is one of the I guess it's the horcrux of all, it's the crux of all electrical engineering. And it goes like this. V is equal to I times R. Voltage is equal to current times resistance. That is one you will need to know. It also has two additional other forms that can be rearranged algebraically. V over R is equal to I, and V over I is equal to R. Next up is the power formula. P is equal to V times I. Now, you'll notice, back up at the top of the lecture notes, that I have joules per coulomb here. I'll actually just use the pointer. Joules per coulomb here, coulombs per second here, and joules per second here. So let's see if we can figure out where power comes from, units-wise. It's in units of watts, and we know that watts are joules per second. But if we have voltage times current, then we can say we have joules per coulomb times coulombs per second. And as you can see, those two coulombs will cancel out, and you get joules per second, also known as watts. We will be using watts explicitly in our lecture series here. Voltage division and current division. I am not going to do too much explanation with these two, but we will talk about these after we've talked about KVL and KCl in detail. And we will come up with these formulas, but I'm going to go ahead and write them out here for your convenience. We have Vin is equal to, V out is equal to Vin times R2 over R1 plus R2. And then in this case, I2 is equal to IS times R1 over R1 plus R2. Again, we will come back to these later, so I know you're not entirely certain where those come from, but an important aside for those of you who are here to learn a little bit more about the context of fire alarm in circuits, or circuits in fire alarm rather, this concept of voltage division, this voltage divider formula, very useful when trying to draw out when trying to design a zone circuit or a NAC circuit. The concept of the end-of-line resistor and the base resistor in the panel comes from voltage division. Now KVL and KCl, you might not understand these formulas either just yet, but KVL stands for Kirchhoff's voltage law. Now, the Kirchhoff's voltage law states that all voltages in a closed loop must add to equal 0. So we're going to represent that by saying the sum, that's what this sigma symbol means, the sum of n equals 0 to max, max being because we don't really know how many voltages are in any given loop, but from n equals 0 to the maximum number of elements in a loop of voltages, V sub n, is equal to 0. This in physics is known as the loop rule. So if you want to know a little bit more about where this comes from, take a look at Khan Academy. They have some pretty decent resources explaining the loop rule, as well as the node rule, which is also known as KCl, or Kirchhoff's current law. Now this states the sum of all currents entering a node must be equal to all of the currents leaving a node, or likewise, all of the currents entering and leaving a node must sum to 0. So we'll write that out with another summation symbol. Let me draw a nicer one. In must be equal to I out. There we go. And this, in physics, is called the node rule. Again, Khan Academy has some great resources for this. Speaking of resources, you may notice at some point during this lecture series that there are some math concepts that are going to be used in here from calculus, both Calculus 1 and Calculus 2. And you may not have taken calculus yet. Now, I am not going to take the time to teach those concepts in this particular lecture series, but if you find yourself lost and don't really know where to go, and I use calculus in one of my videos, I will leave a link in the description to where you can find some resources that may help you learn those calculus concepts. There is a professor at a university on YouTube. He has a YouTube page called Professor Leonard. He is a fantastic lecturer, and if you have the time to dedicate to watching some of his videos, highly recommend it. It helped me in my calculus pursuit while I was in calculus classes in college. Anyway, just that little note aside, I will go ahead and leave a link to his YouTube channel in the description for you, so I hope you guys will make use of that resource as well. As well as physics concepts as well. Highly recommend you look into some physics concepts related to electric fields, magnetic fields, and circuits in general, as that may help you better understand where all of this stuff comes from. Now, I know we have resistive circuits written out here, but there's one thing I do want to talk about before we get too far into this. And that's a couple things that you're going to need to know about voltage, current, and resistance. Now, we talked about Ohm's Law up here. V is equal to I times R, and I think I'm going to draw out this little diagram here to try and help you guys visualize what this really means. Let's say we have a pipe, and in this pipe, there is some water flowing. Now, voltage, in this case, is going to be analogous to the pressure on the water causing the water to flow. So, call this voltage, creating pressure. And then the actual flow of the water, I'll draw it out here with some arrows, use these bigger arrows, that is going to be current. So current is going to be the flow of the water in this system, and voltage is going to be the pressure pushing it along. Now, what do you think will happen if we put a reducer on this pipe and make the area of the diameter of the pipe smaller? Well, change the size there. I don't like that that's leaking out. Well, one might intuitively say that the pressure is going to increase. So voltage is going to go up, and the rate of flow is going to decrease. So I is going to go down. Now, something I did not mention to you earlier is that resistance, and this is from physics, resistance is derived from or is directly proportional to 1 divided by the cross-sectional area, A, of a wire. And we can see that this is the case here in the pipe. As we decrease the area, the resistance increased. Likewise, if we decrease resistance, that means the cross-sectional area is going to be bigger. Now, for those of you who are electricians, this is why we have different gauges of wire. Sometimes we need thicker wire to be able to handle with a lower resistance to be able to handle as much current as we want to run through it without it heating up too much. So just keep that in mind, that lower resistance means that the wire is probably bigger. So we'll go ahead and actually, you know what, I'll leave that there. And I will move this up here. Did not want to do that. Move this up here. Last thing I want to say about current before we move on is that current was defined as the flow of positively charged particles when it was first discovered. However, we've come to find in physics that current is actually the movement of electrons or negatively charged particles. Now, in circuit analysis, we continue to use the definition of positively charged particles moving through resistive objects as our definition of current. So just keep that in mind. Current, as we define it, conventional current, is the flow of positively charged particles. All right. With that being said, I think we're ready to move on to start tackling some of these resistive circuits. So take a pause in the video real quick and see if you can identify the elements that are in this first circuit. If you said that this here was an independent voltage source and this was a resistor, you would be correct. A couple things to note that are going on here. You'll see this plus and minus here, and this V1. This is indicating that the voltage across this resistor, or between this point and this point, is the same as the voltage of this source. This is also notated by this V1 up here. Something else to note about voltage, that voltage is not just a measurement at a single point. It is a measurement between 2 points. So you cannot have just a floating voltage at one singular point. It has to be referenced to something else. So when you see this little notation up here, V1 and then a dot, that does not mean that there's only voltage at that point. That means it's voltage with respect to ground, which is this guy right here. This is the symbol for ground. Now, first we're going to attack these symbolically, as I'm a firm believer that doing things symbolically is the best way to learn them and the best way to derive formulas. So let's go ahead and take a look and see if we can't figure out a formula using what we know that would give us the the current through R1. Well, we know that R1 has a voltage across it of V1, so we can say that R1 is equal to V1 divided by I1, since we know that R is equal to V over I. Now, let's rearrange this to solve for I1. I1 is equal to V1 divided by R1. Now let's apply some values to these elements of the circuit, and we will solve for a number. So let's say V1 is equal to 10 volts and R1 is equal to 10 ohms. Now, if we want to find I1, we just found the formula for I1. I1 is equal to 10 volts divided by 10 ohms, which is equal to 1 amp. So if these were the numbers for the problem and you had found this formula, this would be the correct answer. Pretty straightforward. That's how you use Ohm's law. So let's see if we can extend that to find V out of this circuit. So find V out. Couple things you need to know about circuits, and since I have both of these circuit diagrams here, I will use these to my advantage. These two resistors are connected by a single point. Now this right here is called a node, and a node is defined as a connection between two or more circuit elements at one point. Now, when a node has explicitly one leg going in and one leg coming out, we say that the two elements whose legs are connected together are in series with one another. Whereas when each end of a component shares a node with another element of a component, we say they are in parallel. So these two have both ends connected to each other's, whereas these share a singular end. So this is a series circuit, and this is a parallel circuit. Being able to identify that is going to be very useful in your circuit analysis endeavors, as it will help you simplify circuits. We will talk about resistor simplification in the next video. For now, let's use what we know to find V out. First, we're going to do it symbolically. So we know that this voltage source is going to produce a value V1 at this node with reference to ground. We also know that these two resistors are going to draw some current I1. Something else to note about series or components connected in series is that they will have the same current running through them. So this I1 here is also going to flow in the only direction that it can back to ground. Which means that I1 is also going through R2. So let's use that knowledge to find V out. Well, if we know the value of I1 and we know the value of R2, then we can find V out, because we know that V out is going to be equal to I times R. So I1 times R2. Now, how do we find I1? Well, let's write an expression for I1 in terms of the circuit we were given. I1 is going to be, we're going to have to write an equation that expresses these two resistors in terms of one resistance. So let's say, since these are in series, that these resistances are going to add. So R total, or RT, is equal to R1 plus R2. Now, if I simplify those two resistors into one resistor, then I'm going to have a circuit that looks very, very similar to this. So how did we find I1 in this circuit? We took V1 divided by R1. In this case, we're going to say that I1 is equal to V1 divided by RT, which is equal to V1 divided by R1 plus R2. Now, we can simplify that even further using these two equations. We can get rid of the need to find I1 altogether by saying that Vout is equal to, and now we have I1 and R2. Let's replace this I1 with this expression here. So we'll say V1 divided by R1 plus R2 times R2. And boy, does that look a lot like this voltage divider equation that we talked about earlier. That's because this series circuit here is a voltage divider. And this right here is a current divider. Now let's apply some values just to make sure that these are the same. So let's say we have, let's use the same values as last time for voltage. So V1 is equal to 10 volts. R1 is equal to 3 ohms. And R2 is equal to 7 ohms. Well, I1, let's start by finding I1. I1 is equal to V1, so 10, divided by R1 plus R2, which is also 10, which is equal to 1 amp. Now, if we know that this is equal to 1 amp, we can plug that 1 amp back into this formula here, and we can say that Vout is equal to 1 amp times 7 ohms, which is equal to 7 volts. Now, we move some of this stuff around, make our lives a little bit easier here. Now let's try this other formula we just found, this voltage division formula, and let's find Vout this time with that. So Vout is equal to 10 volts divided by 10 ohms times 7 ohms, which once again gives us 7 volts. So as you can see, the voltage divider equation works. Moving down to the current divider, we already know, and we don't need the current divider equation here to find I2, because we have a simpler way to do it. So out here, let's go ahead and define this current as IS. We define currents with arrows here. Now you can define the current in any direction that you want to. So you can define, I could have defined I1 in the opposite direction, going this way. The only difference when I solve the circuit is that that current is going to turn out to be negative. Now, a negative current just means it's flowing in the opposite direction from which we predicted. So we will talk about that when we get into circuit analysis in a lecture or two from now. But anyway, as we continue on, let's go ahead and try and find I2. Well, we know that the voltage here is V1, which means the voltage here is also V1, since these are all ideal wires. So we know, using Ohm's law, that I2 is equal to V1 divided by R2. Now, if we give the values V1 is equal to 10 volts, done that too much today, R1 is equal to 100 ohms, and R2 is equal to 1,000 ohms. And we know R2 is 1,000 ohms now. 10 divided by 1,000, knock those zeros off there, is 1 over 100, which is equal to 10 milliamps, which is equal to 0.01 amps. Now, if we use that current divider formula from earlier, we would have had to simplify the circuit and found IS first. So just be careful that when I give you these formulas up here, that you don't immediately assume you need to use the formula, or that the formula is the easiest way to solve the circuit. There are many ways to skin a cat in this particular instance, and however you choose to do it, as long as the method works for you, then it is an acceptable method. Last thing I want to talk about in this particular lecture is the passive sign convention. Now, we talked about earlier that current was the flow of positively charged particles for us. Now, I want you to take a second and take a gander at these two diagrams here before we talk about Mr. Voltage over here. And I want you guys to tell me, or at least take a moment to pause, which of these two configurations do you believe would produce a positive current? Does current flowing into the positive terminal or the negative terminal produce a positive current? If you said that this guy right here was going to give you the positive current, you would be correct, meaning that this guy over here is going to produce a negative current. And of course, that's by our definition earlier, that current is the flow of positively charged particles. This is because we consider the positive terminal to be an area of high potential and this minus terminal to be an area of low potential. So let's talk about Mr. Voltage over here. Mr. Voltage is applying pressure to this rock, this beautifully drawn rock, and it is going to move down this hill. It's not going to take nearly as much effort for Mr. Voltage to push this downhill as it would for him to grunt his way up and possibly get crushed by this abhorrently large boulder. So we try and take this same analogy and apply it to circuits. We'd like to think that it's much easier for current to flow from an area of high potential to an area of low potential. This will be a very important concept to understand when we get to the power portion of this lecture series. So next time, we'll start learning a couple of new tricks for how we can make our circuit analysis lives easier. But for the time being, this is all I have for you for the first lecture video. So next time, I guess I'll go ahead and write it out here so I don't forget what I have planned to do. We're going to go over resistor simplification. After that, we will go into KVL and KCl. Now, these may actually end up being separate videos depending on how long they are. After we cover those two, we will go into the branch current method, followed by the nodal analysis method. And I'm not going to teach mesh current analysis because I think it's stupid, but if you can avoid doing mesh analysis, avoid doing mesh analysis. You may have to learn it in college like I did, but it's really not too bad. Not really a whole lot different than KVL and KCl, branch current method, and the node voltage method. Anyhow, that's all speculation of the future. I hope you guys enjoyed this video and got something out of it. If you did, leave a like down below, leave a comment if you have any feedback for me, or if you just want to tell me good job and pat me on the back, I would appreciate the validation. Anyhow, I hope that everybody got something out of this. Hope you guys found it useful. And with that being said, I hope to see you guys in the next video. So thank you for watching, and have a good day.